Welcome to ECEN 215, Principles of Electrical Engineering. Today we're going to talk about an introduction to logic gates. So what we have done so far, we have introduced digital design, a concept of binary numbers, encoding a binary, talking about different switching technology. We introduced functions of binary values using Boolean algebra. And so now we have, say, a function that we have defined, but how do we turn that into an actual physical circuit? Well, this is what we're going to call logic gates. So let's go ahead and get started on this. So let's just kind of do a little review of a Boolean function. So we have multiple different ways we can represent Boolean functions. So as we're going to see here, there are 7 representations that we can do. First of all, we have the English phrase, in this case, that represents a particular line of thought. F outputs 1 when A is equal to 0 and B is equal to 0, or when A is equal to 0 and B is equal to 1. A little long-winded, but that is the function. So we have the function F, and that represents our first thing. Then we can re-represent this. F outputs 1 when A is equal to 0, regardless of B's values. In other words, we've transformed this a little bit and kind of cleaned it up and kind of reduced it into a new form. We can also represent this as an equation, F with A and B as variables, and as A prime, B prime, or A prime, B, or just equation 2 here, using the English phrase 2, just A naught, or A prime. Then we can also reduce this into a circuit of what is going to be known as logic gates that actually implement the function. And that's what we're going to be focusing on in this topic. And of course, we have the truth table. So here we have the truth table. And a truth table, again, as we kind of talked about in one of the earlier topics on the Introduction to Digital Design, is all of the various input possibilities, which again, we have variables A and B are our variables, our inputs. And because of that, there are 2 to the number of variables, or 2 to the number of inputs possibilities. So because of that, we have, in this case, 2 to the 2, so there are 4 possibilities. There's possibility 1, 2, 3, and 4. I usually represent 0, 1, 2, and 3 because it's, it's just counting and starting at 0. So there are 4 possible possibilities of this function. And so you write down all those possibilities. You got possibility 0, 0, 0, 1, 1, 0, and 1, 1. And of course, you evaluate the function in each one of these. So you can evaluate this function or this function. And since it is simply not A or A prime, then we look at A. A is 0 here, so therefore F must be equal to 1. Here we have A is equal to 1, so therefore the output is 0. It's as simple as that. So again, the truth tables is just a representation of a Boolean function with all the possible combinations. For 2 inputs, we have 4 rows. 3 inputs, it's 8 rows. 4 inputs, it's 16 rows. So again, that's just 2 to n, where n is equal to the number of inputs, and this equals the number of rows. So to just kind of an idea of what these truth tables look like. It's all of the possibilities. And what I do is, if you're going to create it, I always put it, things in order, A, B, C, for instance, or A, B, C, D, and then you just start counting up in binary. And the way to note this is just that this is constantly oscillating between 0 and 1, and this one is every other one, so on and so forth. And you notice this is now a group of 4 zeros with another group of 4 ones. And this here, this next one, so it's always half. You'll notice this. This oscillates at half the frequency of this one, and this oscillates at half the frequency here. So if you want to find a way to quickly do this. Another way to represent this, by the way, since this is 4, this could be a hexadecimal, and this is 0 through F, where this right here is A. This is 9. So right here we have a truth table, and we're going to use that to define function ABC. That is 1 when ABC is 5 or greater in binary. So ABC represents a number, so we have 0, 1, 2, 3, 4, 5, 6, and 7. So that's the values we have. And so we want to represent, this is a 1 when ABC is 5 or greater. So if that's the case, we have 5 or greater, so therefore this needs to be a 1, this is a 1, and this is a 1, and the rest of these are 0. So now we have that, then we just need to look at what's happening here, and we can come up with a function. So all of this must be equal to 0, and all these are going to be 1. So we can write this, if we wanted to, as a sum of products. And by the way, this is the reason why we do this, is all we have to do is look at each one of these rows and simply OR them together. So, and we only need to pay attention to where it goes 1. So here we have F is the first one, A1, B0. So we're looking at here first. So if you will, 101 plus, and then it's going to be the next term, 110, or 111 is equal to F. But written in variables, it would be A, B prime, C. So that would be this one, and this one. Plus, we have A, B, C prime. That's this one here. And then the final term, this one here, is just A, B, C. Now let's just look at logic gates. So we have all of these Boolean algebra that we've looked at. And say we have a function here, we have C is equal to AB. That's our function. So we can represent that with a logic gate. This is actually, you can buy an integrated circuit that implements this particular function. It has 2 inputs and 1 output. And the output function is equal to the Boolean algebra, C is equal to AB. So this has a simple truth table, as you've already seen. The only time that F, or in this case the output C, is a 1 is if A and B are both 1. So that's a 2-input AND gate. Correspondingly, you can have a 3-input AND gate, and it looks like this, where you have function output D, where this is F, the output is equal to D, which is A, B, C. And since we have 3 inputs, we would have now 8 rows and have 8 possibilities. And the only one that is a 1 is the possibility because of the function. We have A, B, and C, which happens here. OR gates. Well, now we're implementing the function A or B. And that's represented by this symbol here. And that represents the OR gate. And so simply, if you wanted to have A or B, its truth table being this, where F is equal to 1 when it's A or B is 1, you would use this symbol to represent that. And of course, you can also have a 3-input version, which would have, of course, at the same time, you could have A, B, and C coming into the inputs. And of course, this would end up with a truth table that's A, B, and C, with C, or now D is the output, excuse me. D is the output, and there would be, again, 2 to the 3, 8 rows. And of course, the first one is 0, which would be a 0. And then from here, 0, 0, 1 would be a 1. or 1, 1, 1, and it's all ones all the time. The only time that it is a 0 is when, in this case, A and B are both 0. Which, by the way, De Morgan's law works with this. So if you wanted the inverse logic of F, this would become the AND gate in an inverse logic. So that's out of a side note there. An inverter, this is implementing a NOT or A prime or A with a line above it. And its truth table is pretty obvious. It's just the opposite of A. And that's represented by this symbol here. Notice it has this little dot on the front of it. That is representing the inverse. Sometimes you can represent this if you're making complicated circuits. You'll see some designers do this where they have A and B, and this is an OR gate, very poorly drawn one. So what this is really representing is A prime or B is equal to C. So sometimes people will stick the dot on an input or something. So now we want to convert our logical Boolean algebra into an actual logic gate. And it's something, this is the kind of stuff you're going to be asked for on a test. You're going to be given a specific function. You're going to say, how do you convert this over? This is also on the homework. So here we're given this function. We have A and not B or not C. So just kind of reduce this into a little bit more cleaner form. We have A and not, so we have this, B and not C, correct? So that's one way to do it. We can also distribute this, by the way. And it's not, and this is actually a not of that, not B or not C. So we can just do the inverse of this, by the way, and we can get A, and we end up with B prime C. And then we can redistribute this and do A, B prime, C. Is one way that we can just write these equations. So we can also just go ahead and create the function literally as it says here, which looks like this. So what we did here is we created F as our output, and we have an AND gate. So we looked at this part first. So we have F and we have an A, so we can go ahead and have that. That's pretty straightforward. And then we now need to focus on this portion here. So how do we do that? We put the not symbol in, so we've implemented this portion. Now we have to create the circuit for this, which that's an OR, and we get this from here. So again, kind of highlighting where all this is going. This is the AND. The not is this part, and the OR is this. And so we have B, and we have a not C. So the next thing to be added is just simply the B, and then the not C. So this right here is the logic gate representation of this function. Now, like I said, you can re-simplify this by, reducing the Boolean algebra, but this truly being implemented looks like this. So you always start from the output and you work backwards in input. So here we have F is equal to A and S or D. So again, we start with the F, and then we have A and something. We have A as an input and this right here. So let's go ahead and represent the A and the AND. So we have that part. Then we have the S or D. So that just simply is the ORing of S and D. So fairly straightforward to do this. So again, you're starting with the function f, and you're working backwards. And you're going here and looking at what you can combine first, and then you're doing the S or D. So here we have another one, A and not B, or B and not C. So again, we start with the F, and we have two parentheses here. So we're going to go ahead and look at the ORing first, and then we're going to come back and do these individuals. So you're working back through the Boolean algebra in reverse. So normally you would execute the Boolean algebra by first looking at precedence, which would be inverting the B, doing the and, in other words, doing what's inside the parentheses first, and then finally doing the OR. But when you're creating the Boolean or the logic gate representation of the Boolean algebra, you kind of go backwards through the logic. You start with, in this case, the OR first. So let's go ahead and represent that. And then we've got to implement what's inside the parentheses first. So the A and part. So we represent this part next, the ands. So we have A and that part. Then, of course, the not B is next. And then, of course, we now need to do the same thing here, which is B and not C. And look at what we did here. Since we had B in both cases, we just created a node, electrical node, and we just brought B directly in here. There's no harm. You can also just write B here and not have any of this wire, just have a separate wire. But it's convenient sometimes to go ahead and show this because electrically that is what's happening. Is B is being shared and coming here. This is here is obviously B prime. Of course, this is A, and this is A, B prime here. And it's sometimes helpful to go ahead and write the function out if you're kind of confused, especially if it's a complicated function. Just to go ahead and write what you're doing here. This here is C prime. And the output here is B C prime. And those are your inputs here. And then you can write A prime or AB prime plus BC prime is equal to F, which is what we have up here. So what we looked at is the representation of Boolean functions in various forms and how that can actually be represented by an electrical circuit using logic gates. So in that, we looked at a thing known as truth tables, which represents all the possible inputs for a particular Boolean function or a logic gate and representing what its output function is. So again, if you have 3 inputs, you would end up with 8 possible possibilities for inputs, which give you 8 rows. So it's 2 to the n power. So if n is the number of inputs, so if you only have 1 input, then you have only 2 possible outcomes. If you have 2 inputs, you would have 4. If you have 3 inputs, you would have 8, and 4 inputs, 16, so on and so forth. So use truth tables to represent all the possible outcomes and also how you're able to take a truth table and produce a Boolean function sum of products from that. That's very important to know how to do that by just simply looking at where f becomes 1 and combining the sum of products. Each, in the earlier example where we had A, B, and C, and we had everything greater than equal to 5, how we combined that. Then we looked at basic logic gate circuits, the AND gate, the OR gate, the 3-input AND gate, and of course the NOT gate. And then, of course, we looked at converting Boolean functions to logic gate circuits. So just basically starting with f and working backwards through the Boolean function in the exact opposite order that you would normally go through and converting it into a logic gate circuit. So again, I know this has been a lot of information thrown at you at once here on basic logic design. So please take the time to ponder this information and attend the Q&A to go over further details. Thank you and have a wonderful day.